So, welcome back students. So, last lecture we are basically discussing several functional group based strategies, and I have given you 6 particular points that functional group based strategies will be mainly focused on these particular 6 points. And if you remember the 6 points, we have started the point number 1 where we have discussed functional group based key skeletal disconnection. Means a skeleton of a given molecule was given to you and you have to disconnect the skeleton by having a clear look on the molecular structure, and then you can try to find it out what are the possible transformation you can think of to disconnect the molecule to a suitable intermediate, so that intermediates are commercially available. And we have discussed a complex carbocyclic molecule which can be easily accessed from a cyclohexanone through a combination of aldol and Michael reaction, and finally a late stage carbonyl reduction reaction. So, we will try to continue our discussion on the same topic, and today also we will be talking about this functional group based key skeleton disconnection. So, we will mainly try to disconnect the skeleton of a given molecule based on the functional group present in the target structure. Now, particularly this particular problem which I am now going to discuss, the target molecule having a structure something like this. It is alpha beta unsaturated cyclopentene based aldehyde, and this particular center is having a hanging appendage of a sec butyl group. Though the stereo center was given, we will be not discussing about the stereo center here, but the starting material which was given is a 6 member based cyclohexene. Now, your target is this and your starting material is this. So, this is your key skeleton or the skeleton of the target molecule, and you need to rely on the functional group present in this molecule to have a correlation that how this target molecule will be relating to the starting material through some functional group based disconnection approach. Now, as you see, the alpha beta unsaturated aldehyde, probably the very first disconnection which will be coming to your mind will be something like this. You do a aldol based disconnection if you having a this compound. We just disconnect this particular bond through a aldol dehydration. Now, if this is a purely functional group based approach, as you are having a alpha beta unsaturated aldehyde here, we assume that this ketoaldehyde can be undergoing aldol reaction by generating this carbon ion here to go react here and then aldol dehydration. Now, try to correlate how this compound can be correlated with this particular starting material. Now, you see, only active functional group present in the starting material is the olefinic functional group, and this compound does have a dicarbonyl functionality. So, in principle, if you can think about doing a simple oxidative cleavage. Now, this kind of oxidative cleavage we have discussed earlier, and this oxidative cleavage basically will correlate to the starting material. Means that if you do a oxidative cleavage such as ozonolysis kind of thing, this double bond will be chopped and you get MECO, CH2CH2, 2-methylene. Then your hanging appendage with the proper stereo center will remain unaffected, and then this CH2CHO, CH2CHO. So, see this kind of approaches are absolutely simple, and eventually if I now try to analyze the forward synthesis, you will see that how this forward synthesis can be effectively constructed. So, your starting material is this. Now, I say in the forward pathway we will be first doing a oxidative cleavage of this particular double bond. Now, you can basically think about numerous way you can continue this oxidative cleavage. The pathways are, you can do a ozonolysis reaction, you can do a first make a diol and then you can cleave this diol with sodium periodate the transformation which we have already said, a Johnson-Lamux reaction, Johnson-Lamux oxidation. In addition, you can also do another reaction. You treat this compound with MCPBA to give you the epoxide, then this MCPBA you do a acid hydrolysis, that will give you the diol, and then you cleave with sodium periodate. So, there are many different ways you can chop or you can keep this double bond to basically generate this carbonyl compound or dialdehyde, which is required for the aldol reaction. Now, once you have this dialdehyde, your next step is you can do a simple aldol reaction. Now, here basically you are having ketone and aldehyde. So, you do a simple base mediated reaction to generate this carbon ion here, and then this goes there, you get the aldol dehydration to close the synthesis, and the entire pathway is basically governed by the functional group based skeletal disconnection. Now, important point is whatever starting material we have taken, the particular this stereocenter remain intact here, because the stereocenter was not touched, it was not touched. So, try to figure it out in this way that whenever a key skeleton was given to you, you can basically formulate or you can design the pathway based on your available transformation, and you have to basically correlate that how the starting material which is available to you or which was given to you, you can basically think of that how the starting material can be correlated in a forward pathway to the design target. On the similar line, we will try to do another skeletal disconnection for a target molecule whose structure is a spirocycles. We are talking about the spirocycle ketones, a 6 member and 5 member spirocycle. Here you have a double bond, and this 5 member you have a carbonyl functionality. This is the target molecule, and the starting material which was given to you is this compound, a cyclohexyl based alpha beta unsaturated ester, not alpha beta unsaturated, alpha beta unsaturated esters, sorry, is a alpha beta gamma unsaturated esters. Now, try to correlate these structures. This part is remain as it is in the starting material. Okay. Only thing is the CO, this CO. So, basically you have to introduce this 1, 2, 3. This is a kind of a 3 carbon extension you need to do. So, this is I called a skeletal disconnection. So, now if I do a very conventional retro, probably the retro or the transformations all of you know it. If I say you are having this compound, this diester. So, basically what we are trying to do, you just made this disconnection, because the starting material it is already having this framework which is C double bond O X. So, this part is having the starting material. So, you want to make a new carbon carbon bond here, then you can close these things at this end with the leaving aptitude of this OET or the ethoxy group. So, basically you need to make 2 bonds here. This is the one bond you are trying to make it here, and this is the another bond you would be trying to make it here. Now, if you see the disconnection which you have basically proposed here is kind of a Dickman type of reaction. It is a Dickman type of transformation which probably all of us know or all of you basically aware of. It is a very standard carbon ion chemistry derived transformation, and usually what happen, if you take this kind of diester, you treat this generated anion which basically collapses here to finally give you a. Now, see you are having a basically a branching here. So, this gives you the spiro thing, and then your CH2 CH2. So, your C double bond remains here, and basically you are trying to make this CO2 ET here. So, this is the new bond you are basically going to make or going to prepare. It is a Dickmann reaction. Now, next from Dickmann you basically do this hydrolysis of this beta keto ester, which will give you the target molecule. That is the forward pathway. Now, how to construct this intermediate which will undergo the Dickmann reaction? This is again simple. We will be using a alkylation based chemistry based on enolate alkylation. We said that this compound is a allylic ester, the starting material, means that these hydrogens are enough acidic. So, what try to do, if you put this compound with a base, you basically will be getting a enolate of this carbonyl. Now, this carbonyl is extremely stabilized, because this is having linked with allylic as well as this carbonyl. Let us make this enolate first and find that. Now, this enolate you can easily trap with some electrophile. The electrophile which we will be using here will basically give you this extra 3 carbon. So, now based on this information you select this electrophile, and you will see the electrophile which you require now having 3 carbon CH2, 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 one end you have a bromo, basically you need a electrophile and this OET. Now, if you do this alkylation, which basically will now give you this CO2 ET and this CH2, 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 CO2 ET. So, this intermediate is what you exactly want, and now once you have this intermediate, you take this intermediate as it is, you take this intermediate and then subject this intermediate to a Dickmann reaction. So, Dickmann reaction normally we say the condition is you treat with a base like sodium ethoxide. So, initially carbonyl abstraction, this carbonyl will basically react with this adjacent carbonyl to give you a spirocycle based compound whose structure will be this. Your remaining task is just to hydrolyze this corresponding ester to get this spirocycle beta keto acid. Beta keto acids are very easy for decarboxylation reaction. You just heat it, they will spontaneously release the corresponding decarboxylated product, which is basically the target molecule which you are looking for. So, eventually see, if you see the whole target and try to correlate the stereochemical, sorry, not stereochemical, if you try to correlate with this particular starting material, you will find that this involves basically 2 bond making. You are making a new carbon carbon bond here, you are making a new carbon carbon bond here. This part was given to you. So, this entire part, this part as well as this part was given to you, and then you make 2 new carbon carbon bonds. The transformations which you basically use in the entire thing, we do a enolate alkylation, and in addition you do another transformation which is very important transformation, Dickmann transformation. So, as I said earlier, this entire transformation based strategies, functional group based strategies, substrate based strategies all are similar, but here basically we have tried to figure it out. This transformation or this disconnection is based on a functional group based approach. That is why you put a carbonyl group, this is the main functional group which was placed in the target, and this carbonyl group was disconnected or was thought to be constructed from this starting material, and then this follows the entire retro pathway, which is also a simple functional group interconversion or functional group addition kind of thing, and that basically completes the entire synthesis in a efficient pathway. In a similar way, we will try to now analyze a molecule whose structure is we will be trying to synthesize this molecule as our next target, which is a bicyclic compound, and I say the starting material which was given to you, the cyclopentanone, is a monocyclic compound. Now, if you see this compound is basically a bicyclic compound, ring 1, ring 2 and alpha beta unsaturated connection here, a double bond here. The starting material was given to you. Now, for this molecule we will be try to devise you two pathway, route 1 and route 2. Coming to route 1. So, coming to route 1, if you do the retro, what we are trying to do? We will trying to do in a different way. We say that we will making this bond in a different way. What is the different way? We will make this new carbon-carbon bond to a reaction which probably we have earlier discussed. It is called Horner-Wadsworth-Emmons reaction. It is kind of a Wittig reaction or Wittig transformation. I said it is a Wittig reaction, and this reaction, if you remember, we have discussed in the earlier slides. Fine. Now, next we will again try to simplify the retro in this way, and now we say that if you having a compound like this, you can basically first do a alkylation with this electrophile. So, what you need to do, you have a starting material which is given to you, you take a one equivalent of base, that will give you the anion here, you react with this electrophile and come to here. Now, this electrophile, now once new carbon-carbon bond has been formed, it is having a phosphonate and you are having a electrophilic carbon. So, now you treat with sodium hydride as a base or other bases, suitable bases for doing the intramolecular Wittig type of reaction, then you find this minus will go here. So, this is a route 1. Now, route 1 I say, if you do not know the intramolecular Horner-Wadsworth reaction, it will be little bit difficult. Two transformation we have used. What are those transformation? What we used? Horner-Wadsworth or Emmons reaction, and we used transformation 2 is enolate alkylation. Similarly, route 2 if you now try to figure it out, we will be having a simplified route. Now, route 2 we say we will be doing it a different way. The initial retro was this, again this same bond, and then now we say if you having a intermediate something like this, you can easily do through a intramolecular aldol reaction. So, the first retro will basically based on a intra-aldol. So, same bond, same disconnection, you can in principle construct through a two similar type of reaction, because this reaction is basically a carbon-carbon bond forming reaction. You can use it through a intramolecular Wittig reaction or a Horner-Wadsworth-Emmons reaction, or you can do a intramolecular aldol reaction. Now, aldol reaction probably all of you are aware of that. So, that is why I said this route is simplified route. Now, the next retro is similar, is based on enolate alkylation. So, what you basically need? You basically need this compound is a monobromoacetone. Acetone, its monobromo derivative. So, if you are having a cyclopentanone react with monobromoacetone through a base, you do the alkylation first, then you do a intra-aldol. Now, out of this route 1 and route 2, if you check it, both the routes are quite feasible, route 1 and route 2, both the routes are quite feasible. Only thing is we can say that route 2 is little bit simple. Simple means the transformations are basically simple transformations. Transformations are simple and easy. Whereas route 1, if you do not know what is Horner-Wadsworth-Emmons reaction, if you do not know, then basically you cannot think about this route. If you do not know, then you cannot think about this transformation. That is a big drawback for this route. But if you know this route, there is a ample opportunity, you can think about that both the routes are in principle, it is quite possible. It is quite possible. Now, next question probably I will rather ask from you people, or you may ask that how this compound can be prepared. This is one of the intermediate or the starting material we have shown in the route 1. Now, actually this can be easily prepared from this kind of compound by a reaction named as Michaelis-Arbuzov reaction. Michaelis-Arbuzov reaction. Now, Arbuzov reaction is basically a very interesting reaction. If you have a alkyl bromide, you react with triethyl phosphite, and then once the reaction is over, you basically get this alkyl phosphonate with the loss of one equivalent of ethyl bromide. The mechanism for this reaction, you can basically go to the scenearchive.com, the website which in the very beginning we have discussed, scenearchive.com, that will basically give you the mechanism of the reaction. And here basically if you take this dibromo compound, react with one equivalent of triethyl phosphite, you will be able to get this bromophosphonate, which is serving as a alkylating agent as well as one end which serve you as a Horner-Wadsworth-Emmons reaction. So, in this way basically you can do a keyed skeletal disconnection, which will also help you for your further and future synthetic challenges. Next, we will be doing a similar kind of skeletal based strategies, and the reaction which you will be now discussing is already known to you. So, probably I assume that this target probably you can able to do, because the information which you shared already in a transformation based approach, the knowledge has been already shared with you. I said you have a target molecule which was this structure, and the starting material which was given is a 3-methyl cyclohexenone, simple starting material. Now, the target was given to you, if you try to correlate the now the target, and it seems to be a target which basically does have a alpha, beta, gamma, delta unsaturated carbonyl compound at the left hand side. And the right hand side is having alpha, beta unsaturated carbonyl compound. Now, we have discussed it many times that whenever you find that you have a gamma delta unsaturated carbonyl compound, the best reaction or best transformation will be Johnson orthoester reagent, Johnson orthoester rearrangement or Johnson-Claisen rearrangement, Johnson-Claisen transformation. So, now we do the skeletal disconnection, we do the skeletal disconnection based on the transformation which we already know. Now, see the transformation, we say that first we will try to introduce this vinyl group, because this vinyl group can be easily constructed. Now, I say this X should be something which will only accept one equivalent of vinyl lithium or vinyl other species. Basically, you need a vinyl species here. So, you basically try to have a vinyl species as your, it basically could be coming from a vinyl lithium or vinyl magnesium bromide, is not it? Now, this is a purely alpha beta gamma delta unsaturated carbonyl compound. If we put X equal to OET, it is a gamma delta unsaturated ester. So, next is very simple to do a Johnson orthoester Claisen kind of transformation. Now, I will now put that if you having this kind of allylic alcohol, you do a Johnson Claisen, then basically you can come with this intermediate. Now, definitely we will explore the forward pathway, then you will see how easy these things can be done. So, this is your starting material. So, now start with the starting material. First reaction is very known to us, is a Lucci reduction. Lucci reduction, the reagent was basically used sodium borohydride and cerium chloride, a combination of a cerium chloride, and then basically you get 1,2 addition of a hydride to give you this allylic alcohol. Okay, it is a Lucci reduction, we have talked it many times. Now, once this Lucci reduction was done, you are basically having a allylic alcohol, is not it? Now, this allylic alcohol is subject to Johnson orthoester Claisen rearrangement. The common reagent is triethyl orthoacetate in presence of a H plus source catalytic amount. Now, as I said, initially you will basically having a this intermediate, which we have already discussed that how this intermediate was formed. Now, subjected to heat, it is a pure 3,3 Claisen rearrangement 1 2 3 1 2 3, and if this reagent or this rearrangement goes, basically you will be now having this compound. Now, ester is a definitely good electrophile and you can react with vinyl grignard or vinyl lithium, but definitely once you react to it, you have to first ester will react with vinyl grignard, that will give you the ketone, then ketone is again reactive. So, basically you will end up with a tertiary alcohol, the reaction will not stop in the ketone step. So, what you need to do, basically hydrolyze this corresponding ester to stop this reaction at acid step. Then the transformation we have already discussed is called Van Rapp ketone synthesis, which will basically first we will prepare the corresponding Van Rapp amide, which is very well known amide, and then you react with vinyl grignard. Does not matter how much equivalent we use, the reaction will always stop at this step, and basically you get this corresponding target molecule. So, if you see the retro altogether, it is a purely combination of very unique transformation. The point is the skeletal disconnection is always there. If you know that target molecule is having a skeleton which is nothing but a alpha beta gamma delta unsaturated ester. Now, this gamma delta unsaturated esters, we already discussed that Johnson Claisen is one of the best reagent or best transformation. So, Johnson Claisen you can basically think of using it, and then Johnson Claisen was done, you get the gamma delta unsaturated ester, then you can do a simple functional group interconversion or functional group addition. Eventually, the initial starting material which was given to you, you need to just do a chemoselective reduction with the help of a Lucci condition, which is sodium borohydride and cerium chloride, to end up with the final target molecule. So, it is basically pretty simple, and we will try to have a few more examples, more things, but the take home message you can take it that transformation is always correlated with the skeleton, and this is also correlated with the functional group. which was present in the particular target molecule. So, initially you see the functional group which were present in the target molecule, right. Then if starting material was given to you is fine, and you try to analyze what are the starting material functional groups are there, and then this functional group is the starting material and functional group is the target, how they can be correlated with some transformation. That should be your main approach. Now, transformation essentially is the main key or key toolbox. So, eventually as I said, the transformation, functional group and starting material, this 3 point is linked with a connecting thread. Until and unless you have these 3 points together, a suitable retro pathway cannot be designed. So, your success of this entire pathway always depends on choosing proper transformation, which will basically correlate. The proper transformation is absolutely essential, proper transformation or proper FGI. Proper FGI is absolutely needed, which is basically correlated with this target and the starting material through a common thread. So, any of this point is missing, the thread cannot be completed or the entire retro pathway cannot be completed. So, the success of a retro pathway always depends how efficiently you can connect your target, the starting material through a proper transformation. Okay. Next week we will be talking about other approaches based on functional group based strategies. Till then, goodbye.